In shots like the one that we're focusing on in this class, it makes sense to use the traditional fracturing and constraint setup, but there are many cases where you don't need to do a whole constraint setup or use constraints at all, and you can get the desired effect out of activation and initial velocity alone. To set up this initial velocity demo, I'm just going to make a copy of our week 3 RBD sim setup and paste that here, and we'll just rename this to initial velocity demo and dive inside. I'm just going to delete all of the caching stuff because for this test we don't really need to cache it out. We're not really using it later. However, I am going to leave all of our activation based on the monster, because when you have objects that are activating throughout the sim, that affects how you apply your initial velocity, and it's important that you get used to that and not just the basic case where it's initial velocity at the start frame of the sim. And now that we're starting to add some more things to our RBD setup, just to keep things a little bit more visually clear for you, I'm going to group some of these various sections. So if I select this whole area that we're using for activation, I'm just going to make a box around that and call it activation, and just shuffle these things around. And that should make this a little bit less visually confusing. Now we're going to use this section at the bottom here and apply our initial velocity values just before the pieces are sent to the sim. And if you refer back to the RBD packed object doc and scroll down in your point attribute options, you'll see that it's just using V and W for the initial linear velocity and angular velocity. Now we can start by just using an attribute randomize to set up our initial velocity and angular. So you can drop this randomize anywhere just before the sim. It doesn't matter too much if it's before the sim attributes wrangle or the promotion or after them. It's kind of up to you. And I'm going to call this randomize V and pull up those parameters. And the attribute name we want to randomize is V for velocity. We can leave this on set value. And we want this to initially just fly away from the center of the building. So if we just look at the orientation of our building relative to X, Y, and Z, it looks like the X direction will work well for our initial velocity. So I'll change the min and max to vary from maybe 10 in X up through 20. And we could also vary Y a little bit as well. Maybe we want to vary Y between -5 and 5. And we can do the same thing for Z, -5 and 5. Now before we run this simulation, I'm going to dive inside the DOPNet and turn off this monster collider object. Because for this test, we don't really want to slow it down at those collisions, and we want to just more directly see what that initial velocity is giving us without it being blocked by our colliders. And if we run a flipbook of this simulation, you'll see we're not getting any initial velocity, everything's just falling straight down, and that's because we haven't turned on initial velocity in our RBD packed object. So go inside the DOPNet, select that RBD packed object, and under initial state, you can turn on inherit velocity from point velocity. It's also worth noting that you can use the inherit velocity point attribute on all of your packed pieces to override on a per piece basis whether they're inheriting that velocity or not. The other option is to leave inherit velocity on everything, and if you don't want certain sections to inherit any, you can just give them an initial V value of 0. And of course you would have to give them an initial W of 0 in that case as well, because this inherit velocity option is used for both the linear and angular. Now if we run a flipbook of our new sim, you can see we are getting some initial velocity on some pieces, but we're only getting it on the pieces that are active at the first frame of our sim. None of the other pieces are using their initial V value. Now it used to be that we had to use a little hack to apply initial velocity to the pieces that activate mid-simulation, and we used to have to use a geometry wrangle and detect when a piece becomes activated, and then add its initial velocity in this geometry wrangle, but thankfully we no longer have to do that. All we have to do is say that our input geometry is animated. And although the building itself isn't moving, if we tell the sim that this geometry is animated, then it will look for and apply that new initial velocity as the pieces activate. So once again, referring back to our RBD packed object point attributes, you can see there's an animated integer that you can set here to specify whether it's animated or not. So on our sim attributes here, where we're currently just setting the activation, I'll also say I at animated equals 1. So now if we rerun our simulation with the pieces set to animated equals 1, you can see now they're all picking up that initial velocity. Sometimes it can be helpful to specify a random multiplier on the velocities as well. So to do that, you can add in another attribute randomize, and I'll call this one vmult, and put that after our random v, and this attribute will be set to v, but instead of setting the value, which would completely overwrite whatever we had set previously, I'm going to set this to multiply. And then for each of these axes, you can set different multipliers. Maybe for the x-axis, I want to set random multipliers of, I don't know, maybe 0.8 and 1.2 just for a little bit of variation. And you could set different multipliers on y and z instead. Maybe we'll do 0.5 and 1.5 for a little extra variety. And this is just something that you can art direct to your heart's content. It's also good to set an initial angular velocity instead, which we can do in the same way that we set our initial v. I'll just set this randomized to be changing our w with the operation set to set, and we'll use much smaller values for our w. Perhaps we can use, I don't know, maybe try somewhere from 5 to 10 degrees. So I'll just set -5 and 5 for all of these. And if you want to change the overall amplitude of either the v or the w, you don't necessarily have to change all your x, y, and z values. You can use the global scale to increase or decrease both of those. So if we wanted twice as much rotation, we could just scale that up to 2. Maybe I'll just try 1.5 now. Now if we play back our simulation, the random velocity multipliers are probably not very obvious, but that initial angular velocity adds quite a bit. It's usually pretty important to have those interesting rotations in your pieces. Now there are lots of ways that you can set up your initial velocity. I'd say there are probably an infinite number of ways of setting that up, and one of my favorite techniques is to use a reference point to set all of the velocities. This is particularly good for an explosion source driving all of your points, but it's useful for lots of other scenarios as well. Now we're going to use a wrangle to set up that initial v. So you can drop in a point wrangle, and I'll call this v from point. And for the reference point, I like to just use a sphere. On your sphere, you can leave the primitive type set to primitive instead of one of the poly or other options. And the sphere primitive is just represented by a single point, which is going to be at the center of that sphere. So I can template display that, and we can move this around to manually position the source of our explosion. Maybe I'll just try putting this somewhere around the center of that building, more or less. And then we can connect that sphere to the second input of our v from point wrangle. And then we'll find the vector from that sphere point to each of our pieces. Now you can use this bit of vex code to calculate the velocity for each of the pieces. It starts by creating a local variable direction, which will be the vector from our reference point to each of the individual pieces. And each position is a vector, and when you subtract the reference position vector from the current piece position vector, that'll give you the vector between those. And of course, the pieces that are further away would have a longer vector than pieces a little bit closer to the reference point. And when we're setting up our initial velocities, it's better to have the magnitude of the vectors all be the same. So when you set the velocity equal to the normalized length of that direction vector, then that'll give us a unit vector to each of those pieces so that the strength of that velocity is consistent between all of them. Now, we ultimately don't want the magnitude of the velocity to be the same on all the pieces, so I'm storing a distance attribute which is calculating the length of each of those direction vectors. And then in the last line of this bit of vex, I'm creating a multiplier based on that distance and using that to scale up and down the overall velocity. Now, part of the reason that I set up a distance attribute instead of using a local variable is so that we can check it in the spreadsheet. If you check those calculated distance values in the spreadsheet, you can see what that range looks like. The range goes from pretty close to 0 up through about 18. So that gives us a good idea of what we can use as our remap values on the distance here. Now, with my initial values I used for the remap here, I set it to use a velocity multiplier of 1 when it's a distance of 0, and 0.05, which is almost no velocity, at a distance of 10. But since our furthest points are more like 18 units away, we can set that to 18. And it's also extremely helpful to visualize these velocities in the viewport. And you can turn on your point velocity display here, but when you're working with packed geometry, sometimes you can't really see those point velocities. So to help display those, I will often add in an add node and then pipe in our v from point wrangle. And when you connect that, you have this option enabled here to delete the geometry but keep the points. However, we still can't really see those velocities very well. If you zoom in real close, you can see there are some little velocity trails in there, but it's pretty difficult to see. So I often will use a wrangle node to help visualize that. So if you just drop in that wrangle, make sure it's a point wrangle, and I'll type in v at v times equals 100. And this will temporarily amp up our velocity values so that the trails are a whole lot easier to see. And with those trails a bit more visible now, we can move our sphere around to get exactly the velocity directions that we want to. It's pretty helpful to be able to see this so quickly and interactively. So if you want a more outward push, you can move your sphere back a bit, or if you want everything to shoot upwards, we can move it a bit down, and this is an extremely art directable technique. And we can also verify that our distance fall off is working nicely because the areas closer to the sphere have a clearly stronger velocity magnitude than these pieces that are further away. And our velocity visualization can be connected anywhere within our network here, so perhaps you want this to display the values after the multiplier as well. So you just pipe in your vmult in there, and you can see that randomized a little bit more nicely. Rename our wrangle to view velocity to keep things nice and clean, and let's see what this version of our sim looks like. Now if you run this new sim, it has some initial velocity, but it's pretty minimal. Our randomized setup that we were using for our previous velocity was using values of 10 to 20 in x, but the way we've set this up, we're using values more like 0 to 1. One convenient way of setting up a new velocity multiplier is to go back to our v from point wrangle, and on this last line where we're multiplying it by the remapped distance, we can just add in an extra multiplier in front of that fit. So let's just try 20 times whatever that fit result is. And then let's see what that new sim looks like. Now this new sim still isn't the prettiest simulation in the world, but you can see that initial velocity technique working correctly. We have those velocities based on that radial direction from our source point, and it's clearly stronger nearer to that source sphere. And like I said earlier, there are a near infinite number of ways that you could set up your initial velocities. Sometimes I like to use velocity based on the rel b box. So if you use a rel bboxvex function, you can get a 0 to 1 value for the position relative to the bounding box in each dimension, and you could use a remapped version of that rel bbox value to set up your initial velocities. And of course, you can always experiment with other ways of setting it up as well.